Okay, before we start, so why don't I point out to some asymmetry in the GNS construction. If you recall, you had a functional phi. So for a normal, we took a faithful normal state. With faithful, then that means the radical is trivial. Faithful means the radical is zero, so you don't have to mod out anything. Already you have an inner product, genuine inner product, positive definite inner product on M, defined by and I'll read exact y hat. And then we use this, so we wanted to look at the mapping y hat going to xy hat. We wanted to say that this was a bounded operator. This was a pi phi x. This representation pi phi was defined by proving that this passage y hat to x, the hat of xy, I should say, that this is bounded. The bounded operator, that's what we've checked. And how did we verify that? For that, we had to verify that the norm of the two norm of xy by which one means the phi of xy star xy. We wanted to prove was less than equal to a constant times the norm of y hat. And how did we do this? We did this because this was equal to phi of y star x y, and because we use the positivity of the map, z going to y star zy is positive. The positivity preserving mapping, so that if I define the map, the psi of z be psi of y star zy, then psi attains its norm at the identity. So that is what. So we went through all that. So the point was that this was bounded by norm x squared times phi of y star y. And this was a crucial thing. So there is an asymmetry in this x and y are not quite the same. For this reason, you see, you can also look at this mapping y hat going to yx hat. That also makes as good sense. the right multiplication operator. But if you try to verify the boundedness of this operator, you'll have a problem. You have to prove that this is smaller than norm y squared times phi of x star x. And that you have no way of doing from just these positivity considerations. And in fact, that won't be true. So the point to be noted is that this may not extend to bounded operator B of n to m phi. That is the natural right action of m on itself will not give you a representation because you define phi like this. But this will be bounded if I define the inner product, if I had defined phi of if I defined the inner product instead, some new inner product phi tilde to be phi of xy star. Then you could go through verification and show that this mapping is a bounded operator. Under this case, I urge you to check out the details that with respect to this two norm, right multiplication will give you a bounded operators. So the problem with defining phi this way or that, and so for this reason, it is the good operators for which both things will hold. In the best of possible worlds, these two are the same. Like if your algebra had been abelian, like L infinity, then these two are the same. So both right action and left action, they're the same thing really. They give you bounded operator in the abelian case. But you don't quite require the algebra to be commutative. You only require this functional to have this property. So a definition. We say tau is a trace on M is functional. Will we only be interested in a priori you're only talking about linear functionals. The linear functional. You call it a trace if tau of xy is tau of yx. All xy. This is called a trace because of the corresponding thing for that you have for matrices. For a matrix, there is a definition of a trace of a matrix, and the crucial property of the trace of a matrix is that trace of xy equals trace of yx. So So an example of such a thing is of course the matrix trace. So example, I can define tau on in Mn star by tau of x equal to summation, I'll just say summation xi. So on Mn this will be an example of a tracial function. And usually we'll be interested in positive trace like this. So let us say for the immediate future, restrict ourselves to attention that, so assume that tau is a faithful, normal. All these words make just as good sense. Tracial state. Tau is actually a trace, you can also call it tracial. Tracial. We earlier defined a trace on B of H, but that is not a function defined on all of B of H. Only on trace class operators it is finitely valued. That trace is not a functional, it is not a state, it is a weight. It is defined only on part of the whole space, but this trace is actually a linear function. So we will find that actually algebras, one-on-one algebras which admit such faithful, normal, tracial states, they are very special. So if M has such a tau, if M admits such a tau, we say M is finite. The finite one-on-one algebra. See, in a finite one-on-one algebra, what you should realize is that you cannot have a non-unitary isometry. Why? Suppose you use an isometry in M, and suppose M is finite. Then what does it say? Then it says that tau of U star U is tau of U star. Okay, okay, but tau of U star U is 1. So let us say, so M is finite means that it has a faithful, normal, tracial state tau. So it is that tau that I am working with. So this is tau of 1, which is 1. Right? But then notice that see u being a partial isometry, being an isometry, it is also a partial isometry. We've talked about partial isometries, right? If u is a partial isometry, that means u star is the projection. In any case, if u is an isometry, u star is the projection onto the range of u. So this is the projection which is below 1. 1 minus u star is positive. This is a projection, so it is positive. And tau of this is 0. That means because tau is faithful and this is positive, it will say that u star must be equal to 1. So if you have an isometry, it must be unitary in a finite one-dimensional. This is the kind of thing that happens in finite dimensions. But in fact, in any one-dimensional algebra which admits a finite trace, any finite one-dimensional algebra, and there exist lots of examples like that, as I hope to show you before this course is over. So there are infinite dimensional things with this property. Which also have the property that the only isometries they have are unitary. There is no room for anything like the unilateral shift there. Okay, so I want to examine the GNS construction when we have M is a finite one-dimensional. That is, I want to examine the GNS construction for a faithful normal tracial state. So we'll assume M is finite. So tau is a faithful normal tracial state on M. This is a very strong condition. This is satisfied, of course, by any commutative one-dimensional algebra, like an infinity mu.
So why it is called finite?
He talked about finite. No, this is finite in the same sense. One cannot be one equivalent to any proper projection. That is, if that didn't make sense, just ignore them. So this finite is okay. And now I want to talk about L2 M tau. I want to look at the GNS construction for tau. And so by definition we have this representation pi tau from M into B of L2 M tau. And when we say GNS, then it means you also have this cyclic vector, which is 1 hat actually. Okay, so the first thing I want to observe is that pi tau is 1 to 1. Why? Because? Huh? Because tau is faithful. So why is that? Because norm of pi, see, pi tau x of 1 hat squared equals tau of x star x. Therefore, if pi tau x is 0, then tau of x star x is 0, so x must be 0. So consequently, I can think of via pi tau, I can think of m as I think of m as sitting inside B of L2 m tau. That is, if I take an x in M, then by definition x acting on a y hat is xy hat. Okay. So let's observe two things. This one hat is a cyclic vector for M by definition. The image under of one hat under all of M is by definition dense in L2. L2M is the completion of M1 hat. So this is cyclic vector. Further, it is more. It is also, this is a separating vector. What does that mean? That means I want to say that x going to x1 hat is 1 to 1. Clearly it's a linear map, so you have to show that the kernel is 0. That follows from the faithfulness of tau. So one hat is a cyclic and separating vector for M. So before proceeding, I just want to make a simple little observation about these two notions. So, lemma. In general, suppose M is some one-arm algebra sitting inside some B of H. It needn't be this finite one-arm algebra or GNS or anything like that. Assume M is sitting inside B of H. Then I want to say that psi is cyclic for M if and only if psi is separating for M prime. They are really saying the same thing in two different ways. So let's look at the implication. Suppose psi is a cyclic vector. Then what does that mean? That means that you are told that m psi is h. Therefore, if x prime psi is 0, by this I will always mean something in m prime. If I take something in m prime, and if it wants to kill psi, I must conclude that that thing must be 0 to start with. That is the separating condition. If x prime psi is 0, that implies that x prime x psi equals x prime psi equals 0 for all x in M. That means x prime kills the dense subspace of H. Therefore, x prime is 0. See, this is similar to that statement that if you take an operator, its range perp is the kernel of the adjoint. So when you're looking at self-adjoint algebras, having a dense range, meaning having a cyclic vector, will be equivalent to something being separating somewhere. This is analogous to that. So the argument is similar for the other direction. So what do I want to say? Suppose I know that psi is cyclic for m prime. So I want to prove this is h. So what do I do? So I take P to be look at the projection onto m psi. Now this by definition is going to be something, it is a projection onto a subspace which is invariant for m. So this must belong to the commutant of m. Right? If I call this P prime, this will be an m prime. And P prime of m psi 1 minus P prime of psi is what? So that is 0. But since this thing was in m prime, the separating assumption would tell you that psi must be 1 minus P prime is 0. That is what you wanted to say. You wanted to say that m psi was everything. Okay, so being cyclic for m is the same as being separating for m prime. So coming back to our GNS situation, that 1 hat was cyclic for m and also separating for m prime, for m. It was cyclic and separating for m. So this lemma will say that similarly it is separating and cyclic for m prime. There is the same, m and m prime have this dual behavior. So we find that Therefore, we find that one had, so this back to a finite M and the traceless state and so on. We find that one hat is cyclic and separating for M and for M prime. Right? Being, because we proved if and only if. It's cyclic for M, so it's separating for M prime. It's separating for M, so it's cyclic for M prime. Okay, so this will be crucial for us. So what? So consider the mapping, define. I'm going to define a mapping J from M psi, so let's call this D. This is the domain of this mapping J. I'm defining a mapping on a certain linear subspace of the Hilbert space, but which is dense in the Hilbert space. I'm defining J, in fact, D into itself by J of x1 hat, not say this is one hat. So I didn't say x1 hat, this is just J of x hat. Equal to x star hat. And now we go back to what I started saying in the beginning of the class. Because this tau is a trace, it follows that tau of x star x, which is norm of x hat, equals tau of xx star, which is the norm of x star hat. Right? So J is conjugate linear norm preserving map of D onto D, clearly, because the adjoint mapping is a bijection. Therefore, J extends to a unique anti-unitary operator. What do we mean by anti-unitary? That means same thing as this. Conjugate linear, norm preserving, onto. Right? Conjugate linear. Norm preserving, isometric, norm preserving. And onto. In fact, we see more. In fact, J squared equals 1. Because J squared is identity on D. On on D, by definition of J, J will send D into itself and it's sending X hat to X star hat, and it will then send X star hat back to X hat. So J squared is identity on D. And so the extension, non-preserving extension, and the continuous extension is the identity. So J squared is the identity mapping. So let me just take this for a second on conjugate linear maps. They have this one little peculiarity you have to get used to. I want to talk about the adjoint of a conjugate linear mapping. In general, suppose A mapping H to H, or can even be H to K. Suppose this is conjugate linear. And bounded. Bounded means norm of the usual definition. Continuity is the same as bounded. The conjugate, the conjugate thing, actually the way you should think of this is okay, now I won't go into that. Okay, suppose A is such a mapping. Then I want to see what A star is. Then A star will be the conjugate linear mapping defined by what? I must have A psi inner product eta So what do you think the answer should be? See, A is conjugate linear. So notice that in this equation, the left hand side is conjugate linear in both psi and eta. Because A is conjugate linear. This is conjugate bilinear actually. So if you want to bring in that A star, what do you think you should have?
A star and delta.
Yeah, you know, there is difference between psi and zeta. So this is the adjoint equation for a conjugate linear mapping. So, see, but J is anti-unitary. See, J, I want to say J equals J star. Why is J equal to J star? Because J squared is 1.
J means the extension.
Yeah, the J that we had in our setup there, that I want to say is self-adjoint. It is a conjugate self-adjoint. If you think of bounded operators, what does it mean to say that a unitary is its own square? That means what is its inverse?
Star.
Huh?
Star.
Because it's unitary, the inverse must be its adjoint. But if its square is 1, that means this adjoint must be itself. The same argument holds for conjugate. What I was going to say earlier is that, see, for any Hilbert space H, you can talk about the conjugate Hilbert space. And this is something where so what is this A Hilbert space with a map with bijection C and H going to C bar in H bar such that I'll call the mapping J. J is unitary, is anti-unitary. What that translates into when you unravel this whole mess of slew of definitions, what it says is that this will satisfy C bar, eta bar will be eta psi. See, this is linear in eta and conjugate linear in psi. Whereas this thing is going to be linear in psi bar, which is conjugate linear in psi, and conjugate linear in eta bar, which means linear in eta. So if you have a Hilbert space, so to say you have a so conjugate Hilbert space is any Hilbert space which admits such a anti-unitary map from H to H bar. Can you think of such an example? That is one of the first theorems you learn in Hilbert space theory. In fact, H star is a candidate for H bar. The least representation. Because everything in H star looks like inner product with psi. So a psi bar here, an eta bar here, will be the functional defined by eta bar of psi equal to psi eta. The bracket thing I was trying to talk about before. And this thing, see, this thing is conjugate linear in eta, as you can see. And the theorem will say that this is the norm of this linear functional is the same as the norm of this vector. That means that this J is an anti-unitary mapping. So that is the first example of an anti-unitary mapping that you see. So whenever you have an anti-unitary map J from okay, see, and also you will notice that this H bar is unique up to unitary equivalence, because you take two anti-unitaries. From H, suppose you have an H1 bar and an H2 bar, two candidates for H bar. You have a J1 and a J2 here which are conjugate, which are anti-unitary. Then if you compose them, if you take J2, J1 inverse, that will be linear, that will be unitary, it will be norm-preserving and linear, and a bijection. So this conjugate Hilbert space is unique up to a unitary. So you shouldn't think of conjugate linear maps as complicated things. They're really nothing but you take any h. So from h bar to h, there is a natural conjugate linear mapping J. This pair of h bar and j is determined up to a unitary. Now, if you have to say that you have a mapping from h to k which is conjugate linear, means that if you define this composite as a bar, then a bar will be a linear mapping. So there will be a bounded linear mapping, and so when, you will see that this is the correct definition to give for the adjoint. Okay, so enough about the generality. So let's go back to our scheme of things. So what was I trying to say? Okay, so I want to prove the analog for non-commutative one-on-one algebras of a certain statement for L infinity that I've been talking about repeatedly. When you think of L infinity as being a subset of L2, it is those which vectors in L2 are actually come from L infinity. The answer is those vectors in L2 which come from L infinity are those vectors or that multiplication by them give you bounded operators on L2. So that was the thing that I've been telling you, this thing. You take an f in L2, then f is in L infinity, if and only if norm of phi f 2 norm, norm of gf 2 norm, less than equal to constant times norm g 2 norm for all g in L infinity. So we do the same thing here. But now we have to be careful about, because things aren't commutative. We say a C in L2M, you can actually say it in any module. Is said to be let me start again. So let psi L2M. Then I want to define pi L, maybe I should call it pi L0 because I am defining it only in a length space. So what does that mean? I want to define it on pi L0 of psi mapping m prime 1 hat. So recall that m prime 1 hat is a dense subspace because 1 hat is cyclic for m prime. So I am going to define a mapping on this space into L2M and define this by an x prime 1 hat goes to. So I want to think of this as drift multiplication by xi. So actually it won't look like drift multiplication, but yeah. I'm talking about L2M tau. So there is my standing assumption. We're working with a finite one-hour algebra with this faithful normal trace tau. The reason for calling in pi L will become clear in a minute. Define pi L0 to be this and say and similar. Okay. Now this mapping is first as that it is defined on a dense set, dense subspace. Why is it defined? Why is it well defined? Because x prime going to x prime, 1 hat is separating for m prime. So this is well defined. Right? 1 hat cyclic and separating for m prime implies pi L0 is densely and well defined. The domain is dense and the prescription is unambiguous. A vector cannot be x prime 1 hat for more than one x prime. So it makes sense to say x prime 1 hat goes to x prime of something. Okay, and we'll say that psi is left bounded I'll just say left bounded if pi L0 psi extends to a bounded operator. That means it is bounded. To a pi L psi in B of L2M. That means there is a constant such that norm of x prime psi. All this says is that there exists a constant k such that norm of x prime psi. Let me put a subscript tau to denote this is the Hilbert space inner product coming from tau. Then this is the norm in L2M. I keep writing L2M rather than L2M tau because tau is kind of fixed. And in interesting cases that I've been used to working with, the trace on M has a unique trace. So L2M is unambiguously defined for those things. So, but anyway, that doesn't need bother you. So what we demand is that this is bounded by constant times norm of x prime 1 hat. What is that? There is tau of x star x prime. Norm of x prime 1 hat. For all x prime and m prime. Okay, so I got a pen of different color, but I don't have it, so I'll just say. So similarly, we define pi r0 this will be defined on m1 hat by x1 hat equals to xi. See, all this, remembering which is m prime will become transparent the moment I finish stating the next lemma and why we're doing all this. And because this cyclic separating for m, that will mean that pi r0 is well defined, is densely and unambiguously defined, and we say it is right bounded if pi r0 extends to bounded operator pi r. That means norm of the exists k positive such that norm of x psi tau less than equal to, that's what I started reading, less than equal to k times norm of x1 hat squared, but that is tau of x star x. The tau was defined on m, not on m prime. So on m prime I can't use the same thing, so that's why. Anyway, so I've given you one complicated definition, but you should recall that or notice that if m was L infinity, then this kind of boundedness, the bounded vector, then left bounded and right bounded are the same then, and being left bounded or right bounded is equivalent to coming from L infinity. And the same was present thing happens here also. So theorem. That psi n to m and the following are equal. Psi is left bounded there exists x in M such that psi equals 6 1 hat in which case then pi L of psi is just x. So the passage from psi to x is that x is pi L psi. Passage from x to psi is that psi is x1 hat. So psi and x determine one another. And
It's not physical.
psi is right bounded. There exists x prime and m prime. X prime 1 hat. And in these two things happen, pi r of x prime of psi is going to be exactly x prime. And all those things are equal. So this is more or less the exact analogy of what happens in the L infinity case. So in any finite one-dimensional algebra this happens, and then I will show you soon that there exist lots of nice examples of these things. Okay, so what do I want to say? So let's prove this.
So, what is the meaning of second statement for L infinity?
What is f within L infinity such that psi is f hat. I take a psi in L2. It is left bounded precisely when it is the hat of something in L infinity. Left and right are the same thing in the abelian case. So those vectors in L2 which give bounded operative, which are left or right bounded, are exactly the things in L infinity. And we saw that L infinity was its own comitant. Okay, so let us see. Suppose psi is left bounded. What does it mean? This, if you look at the definition, this pi L psi is defined on initially on m prime 1 hat. It must be clear because m prime is an algebra. If you apply pi L psi to x prime, y prime 1 hat, see what is this, where will this send x prime, y prime 1 hat under this pi L 0 of psi. X prime y prime is also an M prime. So this will go to X prime y prime psi, which I can think of as X prime of pi L0 psi of y prime 1 hat. In this, imagine that x prime is 1. X prime y prime 1 hat goes to x prime y prime psi, then y prime 1 hat will go to y prime psi. So I'm saying that, see what this says is that pi L psi x prime and x prime pi L psi agree on all things of the form y prime 1 hat. But things like y prime 1 hat are dense, because 1 hat is a cyclic vector for M prime. So what we see is that pi L C is an M prime prime. Which is exactly M. That means pi L C looks like some x in M. Sorry, no, this is x. This is x in M. Pi L C equal to x. That is x in M. If pi L C is x, then what does it mean to say that pi L C is x? It means that x of y prime 1 hat see, think that M commute with M prime. So x y prime 1 hat is the same as y prime x 1 hat. Or seen the other way, what am I trying to say? I'm saying that or let me say such that so here let me say that pi L C is x, and then here I say and then psi equal to x1 hat. I just reverse the order of saying things. There is x prime, so then pi R C equal to x prime, and then C equal to x prime 1 hat. So if I state it this way, then I prove that 1 implies 2. We'll come back to this statement in a minute. See, if pi L C equals, so let's look at the, so this, So I wanted to say rather than this that pi of c equal to x. Yeah. Equal to x in m. Sorry, I'm making a mess of writing this thing. I should have just said pi L c is in M. Rather than there exists x and so if I call pi L c as x, then is it clear what I'm saying? I'm just making a mess of the writing here. To say it is left bounded means that it must be the associated bounded operator pi L psi must be in M.
No x.
Huh?
No x.
It is in M means that it is equal to some x which is in M. The point is that x is unique. Because if I have x1 and x2, which both want to be this pi L c, that means x1 and x2 must agree on m prime 1 hat. But m prime 1 hat is dense. So x1 is unique. So pi L c in M, so there exists unique x in M such that pi L c equal to x. Conversely, if pi L c equal to x, it is clear that psi is left bounded. Because what does it mean to say that pi L c equal to x? Implies that how is this fellow defined? This is going to send a y prime 1 hat is going to be pi L c y prime 1 hat by definition pi L c is going to send y prime 1 hat to x of psi, sorry. What am I saying? Pi L c is going to send this to y prime psi. By definition, pi L c is going to send y prime 1 hat to y prime psi. Okay? But if pi L c equal to x, that means x y prime 1 hat equals y prime psi for all y prime and m prime. If I put y prime equal to 1, I see that psi equal to x1 hat. And if pi L c equal to x, then certainly pi L c is a bounded operator. See, x, this is the same as x y prime 1 hat is the same as y prime x 1 hat, which is y prime c, because x 1 hat is c. So I'm saying, I'm trying to prove the converse. If pi l c is equal to x belongs to M, then C must be left bounded. Why is C left bounded? Because of this chain of, I first observed that x y prime 1 hat equals y prime psi for all y prime and M prime. In particular, x1 hat is psi. And so, since x and M prime compute, I can write this as y prime of x1 hat, which is y prime psi. That
X is bounded, so norm of x, y dash 1 hat is less than equal to some positive number, and norm of y dash 3.
yeah, to say C is left bounded means that pi l psi is a bounded operator.
So
If pi l psi is equal to x, then psi is clearly a left bounded operator. And what this argument shows is that in fact psi has to be equal to x1 hat. So that is that 1 and 2 are equivalent. Now 3 and 4 is really the same thing using the fact that 1 hat is cyclic and separating for M.
Pi l psi is to x, then x1 hat equals to psi.
Yeah.
Why it is bound?
X is an M, no? When I say X is an M, elements of M are bounded operators on N to M. This thing is really a triviality. We're just saying the same thing in different ways. We're saying the same thing. So can I leave the proof that 3 and 4 are equivalent, that it's exactly the same? You use the fact that 1 hat is cyclic and separating for M. So these two are equivalent. Okay, so I need to show that M1 hat is the same as M prime 1 hat.
X, 1 hat.
I want to prove that 2 and 4 are equivalent. See, this the way I said earlier is that, see, the left bounded vectors are exactly things of the form x1 hat. And the right bounded vectors are precisely the vectors of the form x prime 1 hat. So I want to prove that M1 hat and M prime 1 hat are the same. Right? So, running out of paper, so I have to go, I have to reverse the thing. Let me give the theorem on the board. For which I need bring in this. Then this little trick here, just a minute. Using now the J operator will come in crucially. Okay. Okay, I want to use the definition of J. How was J defined? J of x1 hat is x star 1 hat. And that is how the J operator was defined. So I want to observe the following thing. I want to say, I want to see what J x J looks like. Of y1 hat is what? See, J is a conjugate linear operator on L2M, X is a linear operator on M. So I can do the composition. I do first J, then X, then J. To see how this operates, and it is a continuous operator. So it is enough to see what it does on a dense subspace. So I want to see what it does on a y1 hat. So what does it do? What the J does is just like puts the adjoint, right? So this is J x y star 1 hat. Right? Because J y 1 hat is y star 1 hat. This is J of xy star 1 hat. And what is that? That is going to be yx star 1 hat. Right? So what this says is really that if I think of y1 hat as eta, if I just forget about hats and if I just think of y itself, elements of M act as left multiplication. X, y hat is xy is the whole hat. So if I don't put hat, then x acting on y will be xy. But how does jxj act on y? It acts, elements of x act as a left multiplication. But jxj acts as right multiplication by x star. The point I want to make or observe that if you see left multiplication and right multiplication will commute. See, if I take a z jxj and add on a y1 hat. The 1 hat is just decoration, it is just that y. What does jxj do? So it will give you, the z is going along for the right, it will give you yx star 1 hat. and that is going to give z by x star 1 hat. Because this elements of M act by left multiplication. And this is the same as jxj z by 1 hat. I want to take that y and hit it on the right side by x star and on the left side by z. Doesn't matter which order I do it. A left multiplication will commute with the right multiplication. No? What does this do? This will first give you jxj acting on zy 1 hat. And that will be, what does jxj acting on anybody 1 hat do? It takes that somebody and puts x star on the right side. So jxj acting on anything looks like right multiplication by the adjoint. So what this says is that jmj is contained in M prime. I verified that jxjz and zjxj agree on a dense subspace. So they must be the same. So jmj commutes with M. X and Z were completely arbitrary in M. Okay. Okay, so I'll just say what I do next time, and so that all this computation is not wasted. What I will show next time is that this same J operator, actually I should have called this as the J operator for M, because J of x1 hat is x star 1 hat, whereas the J operator for M prime will send x prime 1 hat to x prime star 1 hat. But I'll show that this J is the same as that J. That is, we will show that J x prime 1 hat is equal to x prime star 1 hat.
J index.
Huh?
J index.
No.
J sub index.
No, this J. Forget J some M or M dash. They're the same. I have one operator J on L2M which sends x1 hat to x star 1 hat. I am saying that J will also send x prime 1 hat to x prime star 1 hat. That is not obvious from the definition. Right? We'll verify this. But once you grant me this, then by the same, exactly the same argument, you can show that J, M prime J will be contained in M. The rows of M and M prime will be reversed. But then notice that J squared is identity. So this says that if you apply hit J on both sides, you will have M contained in J M prime J. So in fact you will have an equality here. So the moment I prove this fact, so I'll do this next time. Moment I prove this fact, it will show that J M prime J M J equal to M prime.
It is analogous to that L infinity to dash is L infinity.
Yeah. Yeah. But because M may not be commutative. And what this will tell you is that if you take M, what is M prime acting on one hat? It will be J M J one hat. What is J one hat?
One hand.
Because one is self-adjoint. So this J they can go away. Right? And what is J M1 hat? That is the same as M1 hat. This is all, by this I mean all things will form Jx1 hat, which is all x star 1 hat because M is self-adjoint. This is the same as M1 hat. So we prove that M prime 1 hat and M1 hat are the same. So that will prove that the 2 and 4 that I stated in that proposition are equivalent. Hence all those conditions are equivalent and that is exactly. So next time I'll come back to this and do this properly, and then I'll show you some of the connection between this general nonsense we're doing here with something very concrete, with some nice group theory and connect this with.